Okay, I got your back.
Sorry, Steve.
You okay, Steve?
I'm ready.
Go.
Oh, he wants us to read.
Electric motors.
Oh,
Unit 4, electric motors. Or section cycle, my bad.
Are you gonna read it right, or are you gonna say whatever?
Let's go.
No, go ahead.
Unit 17, types of electric motors.
Objectives. After studying this unit, you should be able to describe the different types of open single-phase motors used to drive fans, compressors, and pumps. Describe the applications of the various types of motors. State which motors have high starting torque. Objectives continued. List the components that cause a motor to have a higher starting torque. Describe a multi-speed permanent split capacitor motor and indicate how the different speeds are obtained. Explain the operation of a three-phase motor. Describe a motor used for a hermetic compressor. Objectives continued. Explain the motor terminal connections in various compressors. Describe the different types of compressors that use hermetic motors. Describe the use of variable speed motors.
Uses of electric motors used to turn fans, pumps, and compressors. Facilitate the circulation of air, water, refrigerant, and other fluids. Motors are designed for particular applications. The cost motor must always be used. Most motors operate on similar principles.
Here you have it. The first cartoon of the PowerPoint.
Parts of an electric motor. Parts. Stator with motor windings, stationary portion of the motor. Rotor, rotating portion of the motor. Bearings allow free rotation of the shaft. End bells, supports, bearings and or shaft. Housing holds all motor components together and facilitates motor mounting.
Okay. So the exploded view, we see that so you remember these. The stationary portion of the motor is the stator. The rotating portion of the motor is the rotor. Okay.
Electric motors and magnetism. Electricity and magnetisms are used to create rotation. Stator has insulated windings called run winding. Rotor may be constructed of bars. Squirrel cage rotor positioned between the run winding. Rotor turns within a magnetic field.
Oh, like that. So that's saying you can make your own motor with a magnet.
Wow. So we're gonna have to have a magnet.
You can produce electricity with 2 magnets.
Yeah, apparently.
Yep.
Enough for what?
Enough to power what? Yeah.
Enough to power a light bulb?
No, that's. I think.
Determining the motor speed. As the number of poles increases, the motor speed decreases. Motor speed RPM equals frequency times 120 divided by number of poles. In the United States, the frequency is 60 hertz. For example, a 2-pole motor will turn at a speed of 60 times 120 divided by 2 equals 7,200 divided by 2 equals 3,600 RPM.
Okay, so the motor speed is determined how?
The frequency times 120 divided by the number of holes.
What's frequency?
I don't think the RPM.
No,
That's the rev per minute.
Revolution per minute?
Yeah,
Second.
revolution.
What?
Per second? Revolutions per second?
No,
Per minute.
frequency.
The frequency?
What's the frequency?
In the United States, it's 60 hertz.
60.
In Europe, it's 50.
Europe is 50.
Why does that
Why is
have
it
to do with
50?
altitude and shit?
Huh?
Does that have to do with altitude and longitude and shit?
No.
No, they use like different.
Okay,
Well,
so,
yeah, they use different.
so on this formula, check this out. On this formula, you don't have to remember that whole formula. All you have to remember is, remember that number, 7,200.
7,200. Okay.
7,200. So if you have a 2-pole motor, it's 3,600 RPM. If you have a 4-pole motor, it's gonna be 1,800. 6-pole, 1,200. 8-pole, 900. Okay, got that? Good.
Determining motor speed continued. The motor will turn at a speed that is lower than the calculated value. Slip equals the difference between calculated and actual motor speed.
Okay, so the actual speed on a 3,600 motor is probably gonna be 3450. 4-pole motor, actual speed is probably gonna be 1725, maybe 1750, 1725. 6-pole could be, most of the time it's 1075, and 8-pole might be 850. 825, it just depends on the motor design and manufacturer, right? Okay, got that?
Start windings enable the motor to start and in the right direction. Start winding has higher resistance than the run winding. The wind with more turns, the wind with smaller diameter wire removed from the active circuit once the motor starts. Starting and running characteristics. List of characteristics. Refrigeration compressors have high starting torque. Starting torque twist force that starts the motor. Lock rotor amperage, LRA. Full load amperage, FLA. Rated load amperage, RLA. The motor may start with unequal pressures across it.
Okay, so lock rotor amperage is the amperage, basically, the amperage when that rotor is locked and you try and start it. That's how many amps it's gonna pull. Usually about 5 to 7 times greater than the running load amps or the full load amps. So the running load and the full load amps are pretty much the same. Okay? You getting all this?
Electrical power supplies. Resistance are furnished with single phase power. House can be supplied power from the transformer. Power feeds into circuit breaker panel or fuse boxes. Electrical power supply continue. Circuit breakers protect each individual circuit. Power is distributed throughout the house. Typical resident panel provide 115 to 230 volt. Commercial and industrial facilities require 3-phase power.
Okay, so we know what this is, we did this, we checked that panel back there, right?
Yeah.
We took off the front, which was called what?
Oh, the
Oh,
yeah.
huh? What?
The
What was
death
it?
front, wasn't it?
The dead guy.
Death? What?
The fish tank.
The dead front.
That's right,
Something like that.
Okay, so this is basically the same thing. I got L1 and L2 coming in, you got neutral. Pow. And then you've got the 115 volt on the single breaker and the 230 volt on the double breaker where it picks up both bus bars. See it? Pow, pow. Wow. Isn't that exciting? I might go back here to this slide. It says circuit breakers protect individual circuits. Each individual circuit. Okay, it's really not a circuit unless something is plugged into it. Right? Not a complete circuit. According to the National Electrical Code and the Electrical Union, circuit breakers are there to protect what? Huh?
Individual circuits?
Humans?
No, there's no circuits. If there's nothing plugged in, it's not. Those circuit breakers in your house are there to protect the wiring. That's it. That's it. Okay, so it doesn't protect that blow dryer that you use. It doesn't protect that microwave that you cook your food in. It doesn't protect that stove. It protects the wiring. Okay? Keeps the wire from getting hot and causing fire. Simple. Okay.
Single phase open motors. Residential motors operate at 115, 208, or 230 volts. Commercial motors operate at voltages up to 460 volts. Some motors are designed to operate at one of two different voltage. Dual voltage motors. Dual voltage motors are wired differently for each voltage. Some motors have reversible rotations.
Okay, so we're gonna learn a lot about motors, because there's a lot to know about motors, okay? So a dual voltage motor, anybody ever deal with one?
Probably have, but don't realize it.
A cooler motor? You have a cooler? 2-speed?
Oh,
Yep. Is it, it's probably dual voltage too. You never put one in, huh?
No, it's single, it's only
Okay. So the dual voltage motor, we know from studying series and parallel circuits, if we put a load, is this in series or parallel? Let's start off there. What is that one? Top one. Series or parallel?
Series. I wanted to say series, because
You said
the
series?
bottom one looks parallel, more parallel than that one. I'm pretty sure it is parallel.
More parallel.
But I'm pretty sure it's a series. Okay, continue.
Probably shouldn't.
Okay. L1 comes in, goes through this load, then it goes through that load, and then it goes right back to L2, right?
Okay, so yeah, I was right there.
So it's series. Who said parallel?
See, I did say series. I was the one that said series. Everybody else said parallel. It made me
Okay,
feel stupid.
so we know so in this wiring, we know from our work with parallel circuits, loads in series, the voltage is divided, right? Right? What'd I say?
I know.
Yeah.
I just said yeah.
So we have a voltage drop across each one of these windings. Are you seeing that? Because they're in series, right?
Mm-hmm.
In parallel, the voltage stays the same. So these are in parallel, so they're actually 115 volt windings. So they're wired in parallel for this voltage, and they're wired in series for the high voltage. That's dual voltage. That's one type of dual voltage, okay? Need a cup of coffee?
Split phase motor. 2 separate motor winding, good running efficiency, medium amount of starting torque. Speed typically ranges from 1,800 to 3,600 RPM. Motor speed is determined by the number of poles. Split is the difference between the calculated and actual motor speeds.
The slip is the difference between those speeds right there, right?
Correct.
Okay, we covered that, right? And there we go again, we cover it again, right? Repetition. Split phase motors. This is the motor that you're gonna deal with the most. Okay, split phase. Split phase, terminology, split phase. Okay? Has 2 separate windings. Has a start winding and a run winding. Okay? We go back to our thing, we have a start winding and we have a run winding. The starter switch, which is the centrifugal switch, on this one, takes out the starting winding once that motor gets up to speed. You hear it when you start your cooler. You hear that click? When you start it up, it clicks, and then when you shut it down, it clicks. When it starts to ramp down.
Okay, yeah.
You've heard that, huh? Wow.
Wow, amazing.
That's a centrifugal switch, and we'll talk more about that when we get to it. But I've got a couple of videos, or a couple of movies.
Movies.
Another PowerPoint.
Another like 90s movies.
You wish. Okay, so here we have a cartoon of a motor, a pictorial, and a ladder diagram, right? Okay, so here's the ladder diagram, and can you tell on the pictorial how many poles there is?
2, 4.
Poles? I want to say 4.
You want to say?
I want to say 4.
Okay.
So I want to say 4, so I'm gonna say 4.
Okay. What if I told you there's only 2?
I'll believe you.
Because each pole has a run winding and a start winding.
Yes.
And then, oh, so the red ones are connected. Okay, I see that.
Okay.
Red with the red and black with the black.
Yeah. And we got a motor back there we can look at. We can actually count the poles. Right? So we'll be able to do all that. There it is. What does that say?
The centrifugal switch, commonly used to open motors to de-energize the start winding, opens its contacts when the motor reaches about 75% of its rated speed. When the contacts open and close, a spark is created, arcing, not used in a refrigerant atmosphere.
Okay, so the centrifugal switch causes an arc when it opens and closes. Okay, so you're not going to see those in a gas station, right? Because das ist Feuerspulen, right?
That's a fire speed.
Feuerspulen. And it's not going to be used inside of a closed refrigerant system. Okay? Got it so far?
The electrical relay,
Electronic.
electronic, yeah, I knew I was wrong. Used to open the start winding after the motor has started. Solid state devices designed to open the start winding circuit when the design speed has been obtained.
Okay, so this is another relay they use to take out the start winding. Now the start winding cannot stay in the circuit because it'll burn itself up. The start winding is only designed to stay in the circuit a short period of time. And that's just to overcome the inertia of being stopped it gives it a little torque, gives it the torque to spin, start spinning, and it also determines which direction it's gonna spin. Okay, so that's what the start winding's for, not meant to stay in the in the circuit. And we'll get into that, but there is one wiring where it does stay in, but I don't wanna confuse you right now.
Capacitor start motors, split phase motor with start and run windings. Start capacitor assists the motor starting by increasing the starting torque. Start capacitor is wired in series with the motor start winding. Start capacitor is removed from the circuit when the start winding is removed. Start capacitor increases the phase.
Okay, so we all know what a start capacitor is? When we had your hands on, remember? Remember the start capacitor? Remember? Remember? Okay, so that's what they're talking about, the start capacitors. It's also not meant to stay in the circuit. Okay? So if you notice on the start capacitors, they have a little hole in the top. No? A little hole, kind of a little hole, and underneath it looked like cardboard. Okay. So you didn't pay attention, okay, that's all right.
Okay, no, it's perfectly fine.
Well, that hole is called a blowhole. So that means that if that capacitor happens to stay in the circuit for any reason, like the contacts on the relay stick, it's gonna blow out that hole and not blow the capacitor apart. Wow. Here's a ladder diagram of a split phase motor with the run winding and the start winding using the start capacitor and the start switch. They're right there in series. So as soon as that thing opens up, this loses power. And it continues to run on the run winding. The motor runs on the run winding. Wow. It starts on the start winding.
Whoa.
And it runs on the run winding.
Crazy.
Okay. Okay.
Capacitor start, capacitor run motors. Most efficient single-phase motor. Often used with belt-driven fans and blowers. Run capacitor improves running efficiency. Run capacitor is in the circuit whenever the motor is energized. Start and run capacitors are wired in parallel. Motor amperage will rise if the run capacitor goes bad.
Okay, so start and run capacitors, they're talking about the other kind of capacitor. Remember the run one? Remember? So here is the diagram where the run capacitor is in the system, is in the circuit. So as this switch opens, check it out. It's opening, it's taking the start capacitor out of the circuit. But the run capacitor stays in the circuit. So now energy is coming back through here and through the start winding while the motor is running. Wow. So it doesn't blow up?
Yeah.
No, it's designed to be in the circuit. That's what it's designed to do. Okay, so you have most of your currents going through the run winding. So you can see all those windings there
Mm-hmm.
compared to these?
Okay.
Yeah. So all the current's going through here, most of it, and then there's a little bit of current that bleeds through there, but not much. Okay?
Permanent split capacitor or PSC motors. Simplest split phase motor, only a run capacitor is used. Low starting torque and good running efficiency. Can be single or multi-speed motors, and multi-speeds have leads for each speed. As resistance decreases, motor speed increases. As resistance increases, motor speed decreases.
Okay, so this is probably gonna be 80% of the motors you're gonna deal with.
Okay,
On split phase, it's gonna be PSC,
PSC.
okay? Simple,
Permanent split.
permanent, just one run capacitor, like in here. This is actually showing a multi-speed motor. So you're gonna come in with L1, you're gonna pick up the start winding, or the run winding, and then the start winding. And your speed is actually gonna be your attachment to the other side, or your L2, or the common, or whatever you're using. If it's, or the neutral. So if it's neutral, it's gonna be 115 volts. If it's L2, it's gonna be 230 volts. So whatever speed, if you see that long run winding, we'll talk about that in a minute. That's for low speed. Okay?
Okay.
Low speed, medium, and high speed. Wow. Break time.
Break.
Break.
So Steve,
Break. Take a break.